So we have, I think, a long day ahead. Do you all have sticky notes? Not yet. Yes, we have a long day ahead. Lots of things to do. So there is one tip that I don't know if it was very explicit if Steve mentioned it explicitly, but whenever you want to do a kind of a non-trivial visualization, there is something you want to display with your data. My first advice would be start with pen and paper. Try to produce the figure that you want to generate with pen and paper with colors. Even if the values are not, you don't know the values, just make them up, make the figure up, illustrating if you have results, if it's significant, the kind of perfect figure that would show the features of the data, the properties that you want to see, and then do the same figure, making up the data, of course, with kind of no significant result. But start doing this with pen and paper, and then you ask yourself, then you can ask yourself, does this figure display the information that I want to communicate? It's very easy to get kind of caught into code and confused by the syntax of a package, especially if it's a new package, and we try here, we try there, and then we get involved into the code, into the syntax of the code, and we kind of forget of the message we want to communicate. And so it becomes very easy to spend hours trying to produce a plot, and then at the end of the day, the plot actually doesn't communicate at all what we want to do. I mean, that's useful because we learn some new syntax, but we must not forget that at the end of the day what matters is what we want to communicate. It's the actual figure we want to show. So today we are going to start with the section called Tools and Plots. And on the program we have to kind of see and explore some data transformations. Learn about plots that we can use to compare samples, such as scatter plots, and use kind of linear modeling to model the relationship between two samples. Then we'll have a section on statistical plots. What kind of plots can we use to kind of visualize the results of our hypothesis testing. And then we have a couple of sections about unsupervised machine learning, such as hierarchical clustering, k-means clustering, PCA, also briefly t-SNE, and learn a little bit about the issues with these methods for high-dimensional data. And then finally a section about heat maps. And then normally the last session today we'll learn about some specific R and bioconductor packages to visualize mass spectrometry and proteomics data. So for this I expect that you have a data directory at hand with all the data sets that we produced yesterday. If not, if you download the data.zip file, it contains all the pre-generated data sets in there. So to start with the transformations, we will need the IPRG3 data. So I'm going to load it here, data IPRG3.RDA. dim IPRG3. So So it's 3027 by 13, names IPRG3. My first column is contains the protein identifiers, and all the other ones contain samples. So I'm going to pick out 2 samples. I'm going to relabel them X and Y, just to simplify or to minimize the amount of typing for now. And so, yeah, I'm going to switch a little bit between base plotting and ggplot2, probably more base plotting, just to quickly produce some figures. For some of the exercise, you'll be asked to use ggplot2 when it's appropriate, depending on the data. So here is this scatter plot where on my x-axis I have the values of x, so that was my second IPRG3 sample, and on my y-axis I have my third IPRG3 sample. And whenever you look at scatter plots, you should always try to see how well the points are scattered around. And in this case, because of the nature of these quantitative values, most values are kind of squashed at the low intensity rate range. We can look at this by, for example, looking at the histogram of X. You see that we have most of our values are very, very low, or calculate the density of X, and then plot this. And I see here, I see an error in density. It's a function I try to call X contains missing values. So if I look at any and A X true, any and A Y true too. So I have missing values in this X and Y. Can everybody read when the code is here at the bottom? Yes. It is, yeah, I want to display figures and the code. So when we had our long data, so this IPRG data in long format, we didn't see any missing values because they are not encoded explicitly, but when we transformed into the wide format, the missing values were apparent. So what I'm going to maybe do here, I'm going to say an A when plotting my density, I could use a function, an a.omit x, and this an a.omit will automatically strip missing values from x. So again, I see here the density distribution of my intensities. So whenever I have situations like this, let me come back here to plot x, y. One transformation that I use very often is a log transformation. So now I would like to have two figures shown next to each other along one row and two columns. So in base plotting, this can be done with par, setting a parameter mf row. And so there are two ways where I could log transform this data. I could do it on the fly, where I log transform, in this case in base 10, x and y. So now my x and y scales are in log 10, so it's 6, 7, 8, 9. But another way would be to specify log equals xy, and then my values are provided as they are, but then it's during the plotting that my my data is transformed and my scale is transformed.
What does the part command do?
Yeah, so par sets general plotting parameters. So for example, well, we can look at question mark par. And we have a whole set of parameters here, such as margins, setting the inner or outer margins, dimensions. This queries, if I remember well, the plots these values where my x and y scales start. So there is a whole range of graphical parameters. And these can be set before plotting with the par function. And this tells that I will want to, this defines the layout, where I want to have one row and two columns. So here we have created this scatter plot for two samples. If we want to automatically create this for more samples, we could use the pairs function. So IPRG3. I'm not going to plot this for all the pairs because there would be too many. Let me still use log here, x, y. So pairs will, so in this case I have 4 samples, 2, 3, 4, 5. Here are the subset columns 2 to 5. Here they are, these are the names of my samples. And it will automatically create this 4x4 matrix and produce all the scatter plots. These scatter plots compare these two samples, this scatter plot compares these two, that one compares these two, and so on. So pairs, easy to use, easy to produce many scatter plots, but quite a bit of space is wasted because we reproduce the same figures in the upper right and the lower left diagonal of the matrix. So if we look at the documentation of pairs, we see that it's possible to control what is displayed in the upper panel and the lower panel of this pair's output. And actually there is also a diagonal panel here where we can control what is displayed along the diagonal. By default, it's the sample names. So our first exercise would be to try to modify this pairs function and the lower panel and the upper panel to modify what you get at the top and lower diagonals, sorry, triangles of the matrix. And so what these upper and lower panels take are functions. Functions of the form x, y. So you can define your own function for lower panel and upper panel and assume that these will take the values along the x-axis and the values along the y-axis. And define your own function that will produce the figure of interest. You can also try panel.smooth. That is a function that, let me check. Yeah. Panel.smooth that is a panel function that is already provided for you that will create a scatter plot and then do some smoothing. And if you look at in the example of the pairs documentation file, there is also an example of panel.core to calculate the correlation between x and y. Okay. So the exercise is to try out this pairs function and try to change the upper panel and lower panel using either this one that comes with R. In the documentation file, there is this other function, panel.core. So it's enough to copy and paste this action that defines the function and rerun pairs. Okay. So could you try that exercise and use your sticky notes, blue when you have tried and are happy with it, or if not, yellow or gold. So to do this, you will need to write something along the lines of pairs, IPRG325, or any samples you're interested in, like we have here, but customize how the upper and or the lower panel. The lower panel are these sets of plots, the upper panel are these sets of plots, how they should be visualized. So without setting this, that is the default visualization scatter plot. Yes?
Do you have to define the log equals xy, or it will keep it?
No, if you don't specify it, it will forget about it and not use it.
So you will get the regular rate.
Yes.
But if you wanted to, you could potentially define it with the log xy and then define the panels as well, right?
Yeah, in your panels, you could have some sort of transformation in your panel function, yes. Okay, I suggest we carry on. So there are, if I look at the help file here of pairs, in the example, here they define a function. I'm not going to explain in details how to define the function, but in this function there is this one line of code here that calculates the correlation between two vectors, x and y, and takes the absolute value. So this is, if you want, the core algorithm of this panel.core function that calculates the correlation. All the rest plays with the parameters, the size of the text, and so on. So you would want to take this code, copy it inside here, so now we can set panel.core to redefine what's going to happen when we plot the upper panel, panel.smooth that comes automatically, it is predefined in R, and this is what we now get. Okay, so lower panel, panel.smooth, we have a scatter plot with a smooth line, the lowest regression, and here is the data that we get in the upper panel. And as you can see, we have missing values. And these missing values appear because if I calculate the correlation, for example, of, I'm going to have two kind of random sets of normal values. My correlation is 0.24 here. But now if I suddenly have one missing value in one of these two vectors, my correlation becomes NA. That's what I think mentioned yesterday. As soon as we have a missing value, we need to be really careful. Some of the missing values are there because that's how mass spectrometry works. We need to be aware of this. But sometimes when we do the calculation, we will produce new missing values. And so maybe in this situation, the easiest would be to say NA dot omit to get rid of all missing values before even starting to plot. And here they are. Okay. Arguably not the most beautiful plot ever, but easy enough to quickly get an idea of these correlations and this happens. Doesn't scale particularly well. I'm not going to try it, but of course if I have 12 samples, there won't be very much to see. But at least it gives me a kind of quick indication of how things work. Oh, and by the way, there is, in the lattice package, there is another function called splom to produce similar figures. And there is a GGLE package and that offers the GG pairs function to produce similar figures with GG plotting. Unfortunately, I tried a couple of days ago GG pairs and it didn't work. And I think that's because there were recent changes in some dependencies, and I mean, this one did not work for me on my computer. But otherwise, you can also have a look at Splunk. Yes.
Can we like some built-in functions for this upper panel and lower panel, like some function that operates on two vectors, which is like a built-in?
Okay. Yes and no, because these functions must not create a new plot. So these functions, so if I do plot 110, 10, 1, for example, calling plot produces a new plot. So it kind of clears my device and starts from scratch. I need to use a function like points that will not clear my device, but add that will add something on top. So it will not regenerate a new figure. So let me, you see when I type, say, plot, it clears up the device and produces a new figure. If I see points, when I say points, it overlays my points here, it doesn't clear it. And so in these panel functions, they must not clear the device, they must use points. Or add information on an existing device. And in this case, my existing device are these kind of different subplots. So if there is a function like panel.smooth that does not create a new device, you can use it. If you write your own, you'll need to be careful to add points and not produce a new plot.
And panel is the object which is calling the coordinate?
Here?
Or it's just the name of the panel.core?
Panel.core, yes, these are functions. These are names of functions. Now, related to the fact that to the distribution of our intensities, we have quite a bit of overplotting. Let me plot, x, y here. And so generally, when we have overplotting, as Stephen alluded to, one way to get around this would be to set an alpha channel. As we have seen yesterday in ggplot2, you can set alpha equals and then a value between 0 and 1. In base plotting, I would define my color. So in RGB, 0 red, 0 green, 0 blue means black. And then my last set of values, for example, 80, would define the level of transparency. Okay. So this means that this produces this figure of transparency in my plots. A better approach would be to use another function called smooth scatter. And smooth scatter is going to bin my data. Let me take the log of this. Log 10. So that's with transparency. For this case, it will look better here. Well, now the surface here is going to be binned. And the number of points in these bins will then be converted into a blue color, either dark blue if I have many points, or lighter blue if I have less points. And the bins that contain only 1 point are then represented by these little points here. So that instead of producing each individual point, I produce this cloud of blueness that represents how many points I have. So smooth scatter is a very useful function for that.
So can you go back to like just the end of that? It's cut off a little bit.
Yes. Yeah, and I'm going on to so PCH defines the point character that is used to plotting. So the default is 1, and these are the empty circles, and 19 would be the filled up circles. By the way, all the scripts that I write here, you will get them at the end.
The smooth scatter works off of the plot, like you needed another plot function before.
No. It works on its own. It's going to create a new device and plot it. So here is a new device. It doesn't work as expected. So I use it like plot on its own, and it will create a device and do my plotting and do the binning for me. It's possible to set different colors or different color palette and so on. Yes?
Taking a step back, this is all R. We've not done anything in ggplot. This is sort of where we start with blank canvas.
Yes. This is
Trying
the
to define myself.
Yes. By the way, ggplot has some geoms to do that kind of plotting, but if we want to do anything in ggplot2, we couldn't pass x and y vectors. We would need a data frame to plot this.
Right.
Yes?
In the past, when you do lower the tunnel, then follow the tunnel, it's supplying the x and y to the tunnel, right?
Pardon?
When you have like like the panel.core function we defined, it's applying the x and y, correct?
Yes.
So if you just do core x, y, why doesn't that work?
Oh, you mean if you call panel.core xy?
No, if you just say core and then x, y, if you define the x, so
You mean core?
yeah.
So this works. The only thing is I get NAs because of the missing values. So omit.na, omit.na. Yes, of course it's na.omit. na.omit. So.
I'm wondering why if you say lower dot panel equals that.
So why I cannot here simply say core?
Yeah.
Yes. Because what core does, it takes two vectors, calculates a correlation, and then returns a vector of length 1. What we really need in here is a function that's going to display something. It's going to plot something. So inside the code, the body of this function, it sets some parameters. It calculates this correlation, the absolute value, but R now contains this number. The rest of this text is going to format it, and then it's going to say text 0.5, 0.5, so the text is going to be added in the middle of this plot, and R is going to be printed. So we need some additional code to display the value that is stored. Core calculates it and returns it, and text is going to print it on the figure. But if you want the core algorithms of this panel.core is this line of code. The rest is preparing and displaying.
Can you give an example of like using an inbuilt function, like maybe the top panel is just a correlation and the bottom panel is the same correlation but it like dots or something? Can we do that?
We'll see that a little bit later.
Okay.
I'll yeah. Later. Another important use of fold changes would be, transformations would be for fold changes. So for example here, I calculate my fold change. Okay, when I divide the values of x divided by the values of y, my log fold change, log 2 fold change. And so let me plot this would be the distribution. This looks a little. This is the distribution of my fold changes, and they are centered around 1, and then everything that represents downward relation is squeezed between 0 and 1. And here all the other ones, transforming these fold changes into a log space, transforms the fold change of 1 to 0. 0 means no change, and then I have a symmetric distribution of my positive and negative fold changes, upward relation and downward relation. So log fold changes are much more easy to work with. So let me now before we look at the linear modeling, when we want to compare two samples, let me produce my pairs plot here. It is, I think, in my opinion, not the best way to look at scatter plots, look at correlations, or even do some linear modeling, as we will see later. Because when we want to look at replication, the correlation here is not the best measure of replication. These are kind of slightly different concepts. So if you want really to compare two samples and see how well they replicate, instead of looking at scatter plots, even in log space, it is maybe better to look at MA plots. So MA plots look at the fold change on the y-axis and the kind of average intensity on the x-axis. So I still have my x and y values here. So let me replicate 1 would be log 2 of x. Replicate 2 would be log 2 of y. Okay. And so my m values would be r1 minus r2. So this is my log 2 fold change. And then my a value on my x-axis would be r1 plus r2 divided by 2. So that's the mean intensity for these two samples. And then if I plot a m, here's what I get. I tend to like grids, so there is a function grid to do that. And I'm also going to add horizontal line at 0. So now 0 means no change. So here I compare two samples, two replicates. Here I have my log fold changes. So if the intensity in two proteins for my samples is exactly the same, only it shows slight differences, they will be displayed here along this horizontal line at 0. Big discrepancies between the samples will be illustrated by points that are towards the top or towards the bottom. And the reason why it's also important to look this against the average intensity is that very often we have a relationship between the intensity, how high or low the measurement is, and the variability in our measurements. So we see that for high intensities or high average intensities, we have much better agreement between the two, the replicated measurements, and we get bigger discrepancies for lower intensities. So this gives a much better idea of how well these were replicated. And the AFI package, one of the packages for microarrays, offers this function ma.plot. It offers this function, but apparently it complains now because I have missing values that we could remove with an a.omit. But producing an MA plot is easy enough by computing a log 2 fold change in the average intensity. Yes?
You have to set the power for every figure you want, power function for every figure you want to plot. It won't reset automatically.
Yes. And so if you want to close the device, you can use the function dev.off, and probably one of these buttons here at the top. But dev.off closes the device that is currently used, and then it automatically resets the parameters, yes. And so the last thing I wanted to show as part of this section is linear modeling. Tilde was here. Sorry, LM. So LM will calculate a linear model between, that I'm going to call LMod here, between two variables. And as part of the summary here, we get a summary of the residuals, which is the difference between the observed values and the kind of modeled values based on our linear relation. And so I can reuse this linear model and add it on my XY plot. It is plot XY. And use the AB line to add this linear model, the result of modeling X as a function of Y. So I suggest we move on from transformation, from comparing samples and linear models to statistical plots. And there is one exercise that will actually answer your question before when we write our own panel functions. There is one challenge, but at the end of the day we have a kind of practice session. So maybe we can keep some of the challenges for that, oops. That would produce a figure like this, pairs. This is the scatter plots. And here would be another panel function that produces these scatter plots that plots the linear model using LMod or LM as was shown before. And then it looks at the residuals, the difference between the actual value and the modeled value, and then highlights the points that are either have residuals greater than the 99th percentile or lower than the first percentile, and then plots them another column. The answers are, of course, available, but we could go through this exercise together. So now I would like to move to the next section, which is statistical plots. And by statistical plots, really what I mean is we have done our statistical analysis, something that was done for the ALL data set. So let me load it here. Load data. And among the feature variables in this ALL data, I have a log4 change, an average expression, my t-statistics, a p-value, and an adjusted p-value. where I compared the BCR negative group against a healthy group. This is using a package called Limma, and the code for this is in the very first chapter, where this data set is created. So I have done the test, but before taking the results for granted, it's advised to look at these p-values and look, how do they distribute, how do they behave, to make sure that whatever conclusion we draw are valid. So let's extract these, and we can do this with the fdata function to extract the data frame, the feature annotation, $p.value. This will return this vector of p-values that were calculated. I'm going to call this PV to save me some typing for later. And the first and probably most important thing to do is to look at the histogram of these p-values. And here is what we have. We see...
Sorry. Which library is the FR labels from?
That's in a package called Biobase. And here's the distribution of these p-values. Now this is a data set with quite a few significant results. And when that's the case, we see a kind of a bump here, an increase in p-value of low p-values. That is the kind of histogram of p-values that you would like to see when you expect to see differential expressed results. But there are a range of different p-value distribution that you could see. And here they are shown in a summary. So here's the anti-conservative y. That's what we want. We want to see an increase in small p-values. This typically indicates that even after adjusting for multiple comparison, we will still keep a certain number of significant p-values. If we obtain a uniform distribution here, this indicates that, at least with the conditions that we had, the number of samples that we had, and so on, there is nothing that will survive adjustment for multiple comparison. Even though if we look at the raw data of the raw p-values, some are small. After adjusting for multiple comparison, nothing will be there. And then there are some other slightly more pathological cases. For example, a bimodal distribution, where we have some p-values that are very small and an enrichment of these. But we also see an enrichment in high p-values. If you see something like that, you should probably stop right away and not proceed with your adjustment for multiple comparison, because this bump here will have a negative effect on your adjustment. So you will lose significant features when you do the adjustment. And you should need to understand why do you have an enrichment in large p-values. Look at these features and why do they produce this? Maybe they have some kind of weird values that make them look like they are very, very much not differentially expressed. Maybe you use the one-tailed test rather than the two-tailed test. But if you see this, it's important to go back and have a diagnostic why there is this increase here. Otherwise, this will have a negative effect on your adjustment of p-values. Same thing here. This is weird. In this case, there is no increase for small p-values, but it is weird to have this enrichment in big p-values. Maybe here the p-values you are looking at are already adjusted. Slightly more weird cases when you have a sparse distribution of p-values. This could be the case if the test used some bootstrapping, kind of resampling, and there weren't enough iterations. And here's a slightly more pathological case. And again, when having something like this, you should definitely stop and try to debug these p-values. But clearly, whatever the distribution of it's important to look at these. Okay? In these cases, after adjustment, you won't get any p-values, so you could argue, oh well, I don't need to look at my p-values if I don't have any significant results. But here, clearly, this will have a negative impact on your adjustment. And so you could lose important genes because of this weird distribution. Another, let me move on here. So another important point an important plot when it comes to assessing the results of your statistical test would be a volcano plot. And the volcano plot, let me see, what are the names of my variables? Yes, the volcano plot looks on the x-axis at, so I have PV, and I'm going to say log fold change is f data dollar log fold change. On the x-axis is my log fold change, and on my y-axis minus log 10 of my p-values, or my adjusted p-values. Let's store my adjusted p-value, which is f data ALL dollar h.p.val. And so the interesting points are those with a large effect, large fold change towards the right and the left, and the small p-value. Small p-value are large, become large values in minus log 10. And so my interesting points here would be those towards the top and the left corners. And the important thing with volcano plots is that we tend to use kind of hard thresholds, like adjusted p-value smaller than 0.05, 0.01, log fold change greater than 1 or minus 0.1, but these are all rather arbitrary thresholds. So I think it's much better to look at the distribution of these scores along 2 dimensions, and don't focus only on one or the other. We can, of course, add a grid line, or say AB line vertical would be C minus 1, 1. To add 2 vertical lines, let's say I'm interested in these 2 thresholds, and then add a horizontal line, which would be minus log 10 of 0.05, if this is a threshold that I'm confident with, or it could even be 0.01, and concentrate on these parts of the plot. But whatever thresholds are used, the most interesting ones will be, here I have a continuous distribution of points. As soon as I have these outliers, these are probably the more interesting points. And even though this one does not have as good value as here, but if I'm interested in differentially expressed downregulation, well, this would clearly be my candidate of interest, irrespective of thresholds. And in the notes, I show some code to color the points based on these thresholds of interest and how to annotate some of the points. So maybe that's something we can come back on later. But I wanted to come and talk about this very interesting concept by D. Cook that is treating the plot as a statistic. So we have seen regressions or linear models just before. And this is a data set, and actually I don't know what this data set relates to. But basically what has been done is that we had this data set, or they had this data set, where they were looking at regression, correlation between two variables, and they did a regression, and maybe some of the original authors of this data set thought, oh, there is an interesting trend in this data. And so what they suggest is, well, let's do some kind of resampling of the data that we have. A certain number of times, let's do resampling and produce and recalculate these correlations, these regressions. And show here these 20 plots. One of them displays the original data, and the 19 others display, resample data with the same data set. Can you spot the original plot? I don't remember which one it is. It is not this one. I think the original plot was here. It doesn't matter. The point is, if we do some resampling with the data and repeat the analysis and generate the same plot, will we be able to spot the one that we thought was interesting? Okay, it's this idea of multiple testing, if you want, but using the plot as a as underlying data. What I have done here, and maybe this is something you could look at the very end, I've done exactly the same thing for this histogram of p-values. So I have scrambled, resampled, permutated the samples in this ALL NEC or VRC NEC data set, and repeated my statistical tests, calculated my p-values, and plotted the histogram of p-values. So I've done it here 11 times, plus the original plot. Can you spot the original distribution of p-values? Kind of uniform. We have seen that this it's not helpful, close to uniform. There is a little bump in small p-values here, but this would not survive adjustment for multiple comparison. So can you spot the one that we had before, the one that would be interesting? If these were 12 different data sets, which one do you think would be the one that would give differential express results? Top right, yes. This is the one that kind of sticks out. These ones are a little bit weird, but this just happens. I resampled my data. Yes. So the one top right here, this is the original data set. So without calculating any enrichment score for small p-values, we can do something like that and make sure that this plot sticks out. So this could also be an interesting exercise if you want to try this out, to regenerate different plots and kind of compare them. And so the last part for this morning would be to look at intersections between visualize intersections. And so for that, I'm going to produce, create a data set. What I'm going to do is I'm going to take the feature names of this ALL. Oh no. Okay, here I use the CRC data set. Let me load it. But it doesn't matter. You can use any data set. If this data set is in the form of a MSN set, then if you use the feature names function, this function will return the names of your proteins, kind of row names of this MSN set. And so what I would like to do now is to sample some of these. And, okay, well here I sample 35. So the sample function will take its first input and then do a permutation. And in this case, it will do a permutation and sample 35 out of these couple of, this is CRC, we had 72. We'll sample 35 proteins out of 72 features. Okay. So this is one way to kind of imagine that we have replicates and we don't always assay the same proteins in every replicate. This is a way to simulate this. Based on the pool of 72 feature names, I sample 35. So I will want to do this. I want to replicate this operation 3 times. And then here simplify equals false because I want to return a list of this. So by running this 3 times, I get a list, 3 sets of the 35 feature names. I'm going to call this X, and to make sure I get the same results, just to make it a little bit easier, I'm going to set a seed. Set seed initiates my kind of random drawing. So for example, let me show here, if I sample 5 values from a normal distribution, and I do this many, many times, I always get 5 new samples. But if now I say set.seed to, for example, an integer to 1, and then I rerun my normal drawing, here's what I get. If I now set it to 1 again, and take 5, you see I start my random sampling from the same seed. This is a way to generate random data sets, which is very useful, for example, to do this kind of statistics with plots, but at least it allows me to control what I get. So here is how I generate this test data set from the CRC. I have a list of 3 replicated samples that I call A, B, and C, and each have 35 feature names, 35 protein names. And so I would like to study the intersection of these. One package that and the typical way we do this.
Opening it up a little.
Oh, yes, okay.
Behind it, I can't.
Sorry. I'll give you a couple of minutes to. So a typical way that we want to kind of visualize and study intersections is using Venn diagrams. And there are different packages that allow us to calculate intersections and represent them as Venn diagrams or Euler diagrams. And one that I find useful is this package, Venerable. And I'm going to calculate the intersection of these with the Venn function. So the Venn function is going to calculate all the intersections as displayed here. So X is my list of length 3, sample A, B, and C. Here they are. And so it displays the results like this. So obviously here I have no sample that is absent in my 3 replicates. This is by design. I have 11 feature names that are present only in the first one, 9 that are only present in the second one, 6 that are present in the first and the second one, 5 that are only present in the third one in C, 10 that are present in A and C, 12 that are present in 11 B and C, and 8 that are present in the intersection of these 3. And this can be visualized by plotting this Venn object that I created with a capital V Venn function.
What is the library Venerable?
Pardon? Where?
The library venerable?
Yes. Oh, so it is not available on CRAN. It's available as a GitHub repository. And I'm going to show you how to install it here. Library. You should have this DevTools package that allows it. It's more flexible to install packages from all over the place. Install _GitHub. And I need to check where it. Let me copy this here. Copy this here. So DevTools install GitHub, and the name of the repository is JS224. Or you can also run the installation script. It has now disappeared. It's biomolvis _install, and it would install it automatically. But otherwise, if you run this, so that is the name of the package, and that is the name of the GitHub user, it will install the package for you. And so here is the kind of visual representation of this intersections, of these intersections. Arguably not the best choice of colors, but then again, it does the job pretty quickly, and it gets what I want. But there is another package to look, and another way, a completely different way of visualizing data, visualizing intersections using so-called offset plots. And the offset R package allows us to produce these offset plots. And so I'm going to create a new variable, x2, and I'm going to say from list x. So from list x is going to take this list x and transform it into an input that offset R will understand. So yesterday I talked about the long format, the wide format, or MSN sets. In this case, offset R has its own input format, and this conversion can be done with the from list, and X is a list. And once we have this, we can look at use the offset function with x2 to produce this figure. So this is an offset plot. And so A, B, and C are the original sets that we had. Let me do the following. V, yes. Okay. So my original sets were A, B, and C, and if you remember, that was by design. Each of them had 35 elements. So we see here 35, 35, 35. If they were of different sizes, this is what we would see here in the bar graph. And then here on the top, we see bar plots that tells us the size of these different intersections. So for example, if we look at 100, so 100 is what is present only in A, and we have 11 feature names that are specific to A. While here, specific to A, which is highlighted by kind of a point, we indeed have 11 features. Specific to B, we have 9. Specific to B, only in B, we 9 here, and only in the third one, only in C, highlighted by this point, is 5. If we now look at the intersection of A and B, highlighted by these 2 points here, and linked with this line, we have 6. A and C, we have 10, so A and C, AC linked by a line, we have 10, and so on. 3, 1, 2, 3. The 3 sets are highlighted here and linked, we have 8. Okay, so it's kind of a completely different way of looking at intersections. I'm going to show you a little movie here. Where is my link? Come on. Yeah. Again. Okay, so here we have a Venn diagram with three sets and their respective intersections. It illustrates kind of in a visual way how this visualization works. And by the way, the author of Upset R, Niels, is going to give a talk tomorrow. So there is it is possible to control the ordering with the order by ordering of the intersections here, order by frequency, or order by degree. Okay, so the degrees here we have intersection of 3, of 2, of 1, and so on. But I'll let you explore this by yourselves. Okay, sets controls which sets to display. But I would like you to explore this by regenerating a new test data set, as was shown here, but not with 3 sets, but with, let's say, 10 sets. Because with 3 sets, I don't think that the offset visualization is really convincing. You know, Venn diagrams still work reasonably well when we have 2 or 3, maybe 4, but clearly more than 4 Venn diagrams don't escape. But, as you'll explore yourself, discover yourself, offset figures still work even when we have more. So could you explore, try Venn if you want, but certainly offset with 10 sets. And so if you rerun this, and instead of running this 3 times, you do it 10 times, okay, then the letters would be 1 to 10, and then you say from list, offset your data set. Offset here. Okay. Repeat this, but now not only with 3 sets, but more. Try 10 or 5, 6. Clearly, if you say 5, 6, you will still be able to produce a Venn diagram, but it will not be helpful at all, I guarantee you. And probably with 10, it will tell you that it can't draw one, at least not in 2 dimensions. Okay? So could you do that until the end, until 10:30, and then we'll have a refreshment break. Yes. So what you might need to do to be able to run this is to load a Mazen base. Yeah. To be able to extract the feature names of an Mazen set. Or what you can of course also do is to use the CRCDF data set. So CRCDF dollar, or at least the one in the long format, because CRCDF is in the wide format. So there you would need to extract the column names of interest. But if you have the one in the long format, you could use that protein column. But don't forget to say unique, please. Then you take the unique protein names that would also go.